Welcome back to day number 2 of vectors. Lead off with problem number 4. It says that we have a particle moving along a curve. We know that this particle is at the point 2,6 at time t equals 1. And we know the dx dt and dy dt. Those have been given to us. Part A is the horizontal movement of the particle to the left or to the right at time t equals 3. Explain how we know. So that's one thing. And then separately, it asks, find the slope of the path of the particle at this time, t equals 3. So really two things, and the first one has to be explained as well. Okay, is the horizontal movement of the particle? Well, that's only going to involve dx dt. So let's try dx dt, and we'll simply plug a 3 in, see if it's positive or negative. If it's positive, the particle will be moving to the right. If it's negative, the particle will be moving to the left. It's that simple. That'll be my explanation. Let's see which way it's going. Okay, plugging in the 3 to this dx dt equation up here is going to give us the square root of 6, that's the 3 plus 3, of course, over e cubed, because that's e to the negative third. You guys, that's positive. Those are both positive numbers. So that's going to be greater than 0. So we just simply have to say, since dx dt is greater than 0, the particle is moving to the right at t equals 3. Okay, that'll be the explain how you know part. And we've also answered left or right. We said it's moving right. So those first two things are done. Let me write that out. All right, so that's complete. Next up, we want to find the slope of the path of the particle at time t equals 3. Well, again, slope is derivative. It's dy dx. In this case, it's dy dt over dx dt. And we know both of them. They're both given to us, so I can just put that right in. And instead of writing t's, I'm going to write 3's in the appropriate locations. And when you type that into your calculator, again, make sure you're in radians. The slope is going to come out to be negative 16.235 or negative 16.236. As you can see, I'm permitted to either round off or truncate. Okay, so that's it for part 4a. 4b asks us to find the x-coordinate of the particle's position at time t equals 5. We saw a similar question to this yesterday. So we're looking for x of 5. So again, we know that the x is 2, but that's when time is 1. So we're going to integrate from 1 to 5, because that'll be how far this particle has moved in that time period from 1 to 5. And we just simply need to integrate the dx dt, which is this. Because it simply says find the x-coordinate. We don't care about the y-coordinate. So that's going to go in there. You can write dx dt or you can write it out. It still does have a little dt at the end, a differential. And we'll just see what that is on the calculator. There's no way to integrate it by hand. When you plug this in, you're going to get 0.7988. And obviously adding the 2, you're going to, again, have two answers, either 2.798 or 2.799. All right, we did it. Moving ahead. For C, I'm asking you for the speed and the acceleration vector of the particle, both when time is 7. Start with the speed. You either know the formula or you don't for speed. Hopefully you know it. Here it is. All right, we want the speed when time is 7. So if we put 7's in here, we can do that on the calculator. So we get it typed in, and we see our answer of 1.507 or 1.508. Again, either one works. If you want to be safe, just round it 4 places, and that way you don't have to worry about rounding incorrectly. And last but not least, for D, I want to know the total distance traveled by the particle from time t equals 1 to time t equals 3. Total distance is simply the integral of speed. Pop that into the calculator. You know how to hit the keys. It's going to come out to 2.278579607. But I don't have to be that crazy. I'm going to 3 places, so it's either 2.278 or 2.279. And that'll be it for problem number 4. Number 5 looks similar to the others that we've done, with one major difference, and that is that in the middle it says dx dt is not explicitly given. And once in a while, College Board will pull this on you, where they tell you one of them and not the other. We have the dy dt, no problem. And so in part A, when they say, hey, find the y-coordinate, we can do that. But later on, this dx dt not being known is going to become a potential issue for us. So we'll cross that bridge when we come to it. First off, part A, let's get the y-coordinate at 4. That's y of 4. We know that at time t equals 3, the y-coordinate is this 9. So we're at 9 plus, and when we integrate, that will tell us how the particle has changed between 3 and 4. And we just use the dy dt, which is the 2 plus sine of t squared. Notice it's sine of t squared, not sine squared of t. Okay. All right, we can integrate that on the calculator. That's the only way to get that. The 9 drops down, of course. And the integral ends up being 1.97357. Which means y of 4 is either 10.973 or 10.974. Part B. At time t equals 3, the value of dx dt is negative 5. So even though dx dt is not explicitly given, we get a little sneak peek of it at least, and that's helpful. Write an equation for the tangent line to the curve at the point x of 3, y of 3. Whenever I want an equation for a tan line, that's easy. I head right to point slope form. I know that when time is 3, that the particle is at the point 5,9. That's a huge help. So it's going to be y minus 9. I don't need parentheses over here, but I like drawing them for some reason. Equals, okay, space for the slope. And then x minus 5. Again, I'm just taking the 5 and the 9 from the point that I know. And now I need the slope at 3. And slope is dy dx, or in this case, it's going to be dy dt over dx dt. This is the slope when time is 3. And luckily, when time is 3, we know what dx dt is. It's negative 5, so that's going to be the denominator. And dy dt is given to us. We just have to take a 3 and plug it into here. So it's going to be 2 plus the sine of 9. And honestly, you could take this and just jam it right in there, and that would be a perfectly fine answer because free response questions do not have to be simplified. It's kind of obnoxious. If you do figure out what this is on a calculator, it'll come out to negative 0.482. Negative 0.482. And that's the equation for the tangent line at time t equals 3. Oh, another question about speed. Wouldn't you know it? Let's get the speed formula written. Okay, the formula for speed, of course, is the square root of dx dt squared plus dy dt squared. The speed has to be positive. And of course, we don't want dx dt and dy dt written out that way because we know what they are at time t equals 3. So we're going to use that instead. Remember that in the last problem it said that dx dt was negative 5 at time t equals 3. So we can use that to our advantage. And that this, again, is going to be, when time is 3, it's going to be 2 plus the sine of 9. And that would be 9 radians. Make sure you're still in radians. Put that into your calculator. You don't have to show the intermediate step. It comes out to square root of 25.679. Hit the square root. And that will be 5.067. And that is your speed. It does not round up. It's 5.067. All right, this leaves us with Part D, and we're all done for the day. For time t is greater than or equal to 3, the tangent line has a slope of 1/2 t plus 1. So they're giving us dy dx here. Okay. And I'm asking you for the acceleration vector when time is 6. And as we know, the acceleration vector would involve 2 derivatives, but we don't really need to take 2 derivatives because we already have dy dt. It's already velocity, so one more derivative would be acceleration. The problem is this dx dt not being explicitly given is now coming back to haunt us again. So we're going to have to work our way through this. The fact that we know dy dx helps. All right, let's work through this patiently. We know that dy dx is 1/2 t plus 1. But I also know that dy dx is dy dt over dx dt. We know that the dy dt in the numerator is actually 2 plus sine of t squared. So we can bring that in instead. All right, so we know what dx dt is then. Dx dt, if you cross multiply, times 1/2 t plus 1 is going to be equal to 2 plus sine of t squared. Therefore, dx dt will be 2 plus sine of t squared over 1/2 t plus 1. Therefore, we know the velocity vector. The velocity vector is just dx dt, comma, dy dt. All right, we've done a lot of work so far. Our goal is to find the acceleration vector when time is 6. Remember, that's what we want to do. We've got the velocity vector. The acceleration vector is simply going to be the derivative of each one of these independently with a 6 plugged in. And we could do that on the calculator. Okay, I typed them in. y1 is actually dx dt, and y2 is dy dt. All right, so we want to take a derivative of each one of those and evaluate said derivative at 6. So here's how we're going to do this. Let me get out of graphing mode. Onto the main screen. Math 8. N derivative, numerical derivative. I'll take the derivative with respect to x, which x is serving as t here. Let's do y1. So variables, vars, y vars, y1. That's the dx dt, you may remember. We're going to evaluate it at x equals 6. That's negative 0.415, and that's not going to round. Okay, so that's the first part of our acceleration vector. And we want to do the exact same thing. I'll just save some keystrokes. I'll get in here and change y1 to y2. And that's going to be negative 1.535 or negative 1.536. So there in green is my answer for the acceleration vector. It's negative 0.415 and negative 1.53. I made it to 4 places just so you know it can be 535 or 536. That's it for 5D. That's it for day number 2. That's it for vectors. Fantastic work, everybody. Hopefully it all made sense and you enjoyed it. BCers, you only have one more section to go. Section 10C is what I called it. It's polar coordinates. Light is at the end of the tunnel. See you all then.